So, good afternoon, everybody. Good morning, rather. Welcome to the last colloquium of this year, 2025. We finish with a big splash. We have a pleasure to host today Chiara Mazzocchi, who did her undergraduate studies in Milano, and then she moved to do her PhD in Mainz, and then a postdoc in the United States, in the state of Tennessee, and back to Milano. And finally, she came to us, to Institute of Experimental Physics and the Nuclear Physics Division, and she will talk about how the tools that she is proficient at can be used to analyze, in this case, as I learned, a Renaissance script. Please.
Thank you. So, actually, this is a little bit different from my day job. I think it's on. Oh, sorry. My day job, which is experimental nuclear physics, but 3 years ago, I got a chance to collaborate as a scientific advisor on a very interesting project, which was related to the conservation of the prayer book that belonged to Mary, Queen of Scots. And the point was that we needed to do as many non-invasive analyses as possible to aid the conservation work. And this analysis is 3D imaging with micro CT. So I will start, I will start to describe what I call the science case and the goal of this project. Tell a bit about the methodology of choice. I know that there are some students in the audience, so I will tell a little bit about micro-CT for those who are not too familiar with it. And then we will go to the measurements, because we did microtomography, but we also did some carbon-14 dating. I have some preliminary results on that. And we did analyze pigments and inks in this amazing manuscript. I will conclude with my summary and outlook towards the future. So you can see here 2 examples of 2 illuminations on the book with prayers on the side page. It's a manuscript made out of vellum with black and red ink writings, illuminations, and you have several incipit letters that are highlighted. And it is an extremely rare example of prayer book with prayers in the female form, which wasn't typical of the time, and was made in the mid-16th century, between 1535 and 1540, for the Abbess of Fontevraud. Sorry for my French, who donated it a few years later to her niece, who was Mary Stuart. And you can see here the monogram that she wrote. At the end of the prayer book, there were empty pages for notes, and there she was writing her own comments, and this is her signature. The book has a long history. So this book was heavily used, and this means that every now and then, let's say 50 to 100 years, it had to be rebound. Vellum is a very delicate material, and it was tearing apart. So we know that the last rebound happened in the late 18th or early 19th century, when several changes were introduced to the structure of the book itself, with the consequence that the book could open for something like 30 degrees, not more. So I have here a mock-up of the book. I cannot show you the original one. I will tell you later where you can see it. So if you can open it something like this, you cannot really put it out for an exposition in a museum, for example. So this is where this project started. So the idea was to do a non-invasive inspection of the state of the spine structure which was necessary before physically operating on the book. Once you cut the thread, for example here on the spine, you lose the information about how it was bound. Visual assessment was done before. Of course, this book was studied. You can see here the silk red thread, which was introduced during this last rebounding, and the book really not opening very much. So from the just visual assessment, it was possible to estimate the structure, the sewing, and to figure out that there was this overcast stitching that was too tight, and it wasn't possible to find out anything more. So crucial information for planning the whole conservation and the restoration work was missing. So with this non-invasive, of course, you don't want to do anything invasive on such an object, scientific analysis, the idea was to gain a deeper insight into the structure of the book spine and understand the binding structure and its history, how it changed over time, with the ultimate goal of providing guidance for the conservation. So, a few general principles about computed tomography, which was the methodology of choice. The word comes from the Greek tomo and graphein, to write and record, so slice and recording slices. It's a radiographic technique. It's the same technique we use in hospitals. So you select a level in the object, and it blurs out the structures below and above the plane. So this is our non-tomographic projected image of such an object, so like a radiography, for example. And if you do slices, you can reconstruct the 3D structure inside. So here are, for example, two cross-sections shown. In a CT, the CT image is basically a matrix of numbers. You have pixels, and since the pixel has a depth, you have a so-called voxel, which represents these small 3D structures. So you end up, when you do a tomography, with an array of a 2D array of pixels, which correspond to the same number of voxels. So the signal intensity in each of the pixels will mirror the material chemical composition and the thickness of the material that the X-rays went through, so the density, basically. So you have an X-ray source, for example, the object in the middle, which is rotating. This is the difference with the medical CT. You can rotate the object in a micro CT rather than having the structure rotating around it, and you can achieve much better resolution. And on the other side is a 2D detector. So what do we measure? As I said, we measure the intensity, the absorption of the X-rays in every pixel. So you have that the intensity, as we know, is exponentially depending on the chemical composition, on the absorption coefficient for the given material, and on the thickness of the material. Of course, if you have more materials present, you are taking all of them into account, and they sum up here in the exponent. So when the X-rays are absorbed, you have our standard effects for absorption of X-rays, and dominant one is photoelectric effect, but you have also absorption due to scattering, Rayleigh and Compton scattering, which means that since the cross-sections for these effects depend on the material and on the energy of the X-rays, how many X-rays will make it through and will be detected by the detector depends on the material itself and carries this information. So as we know, absorption coefficients increase with increasing atomic number. And you can see here an example taken from one of our micro CTs. This is a letter, which I think it's either an O or a letter Q. And you can see that it's much brighter because it's painted, it's drawn with pigments that contain high Z elements. Gold is typical in this kind of manuscripts, but you also can have mercury, which is in the red, vermilion red, the color, iron, which is in a whole series of different pigments, lead as well is in the medium red, it's in the white, and in some types of black. And you can see here, I think I managed to find the correct letter on the manuscript. And for example, what you see here, why this text is more brighter, because there are parts of the text that are written in red. So with heavier elements than the main ink, which is based just on iron. When it comes to this kind of studies, resolution is crucial. So that's why we went for micro CT rather than hospital CT. We actually tried hospital CT but didn't have high enough resolution. Because resolution is due to, let's say, having a good resolution depends on several factors. You can see here, this thing is the X-ray tube. You put at a certain distance your object, and you have the detector on the other side, which is pixelized. So you have the pixel size. And basically, starting from the focal spot, you will have here the voxel size, and then the pixel gets magnified and magnified. One of the key factors in the resolution is the X-ray spot size. So how the focused X-ray spot comes out from the source. So if you have a large spot size, as you can see in this image, you will end up with something blurred. While if you have a small, ideally point-like spot size, your image will be much sharper. So this is the main limitation factor for the achievable resolution. But other factors, as you can see here, the resolution is given by also has important the size of the detector and the pixels. And then there is the geometrical magnification, which depends on the relative distance between the source, the object, and the detector. So if you position your sample close to the source, you will have significant magnification, which means you will have better resolution, because its resolution is inversely proportional to the magnification. If the sample is positioned close to the detector, farther from the X-ray source, you will have minimal magnification and therefore worse resolution. The detector, typical detectors are scintillator detectors that transform the photons generated when the X-rays are interacting with the scintillator into, so the photons, X-ray photons into visible light, which is then detected by, for example, a CCD camera or CMOS image sensor. We are talking about pixel pitch of the order of 5 to 10 micrometers. So this is the global view of how micro-CT works. You have your object, you have your source, the detector on the other side, and then you are rotating it one relative to the other in order to obtain a whole series of two-dimensional images, which are then reconstructed through a set of algorithms into a stack of images. So you're converting to X, Y, Z, to Cartesian coordinates. Your images were taken at different rotation angles. So you have digital to analog conversion, and you end up with your projections that later can also be reconstructed into 3D. But it's better sometimes to work on the projections. So basically, from the mathematical point of view, you are reconstructing, you have to reconstruct an n-dimension function, which is your image. This is a multidimensional inverse problem, which uses the so-called inverse radon transform to reconstruct the 3D image of this unknown object using several 2D projections. And the mathematical basis for the radon transform, which are the basis for tomographic imaging and other types of imaging, were developed already in 1917 by Johann Radon. So like in any problem in physics, in particular in experimental physics, you want to have simulations before you attack the physics case. And that is what we did. We needed to make sure that our imaging, that we could read it correctly, okay? And we used for this simulations mock-up books. I have one here. If you want later, you can see it. Has the same dimensions of the original book, but because we didn't know how the structure inside was, this is a sampler. So there are, as you can see, different pages of different color, which means different thicknesses of the paper and different materials. And there are, maybe they're not very visible, but I show you in a moment, different structures of the binding. So a group of pages are bound with one technique, a group of pages is bound with a different methodology. So historical kind of practices that show that tell us that the expected structure is like in these sketches. So you have these bands, okay, and then you have that the pages are, like this, like one inside the other, with the thread going in and out along the spine, and then they are put together, several bunches. So this is what you see in this, in these drawings, okay? So the blue dots here is the thread going along the spine in this direction, in and out. But in the sampler we put also other, because already from the visual inspection it was obvious that this original structure was not fully preserved, so other types of bindings were introduced. So you can see here this regular sewing technique, and below here you can see a different way. So if you don't have, if you lost, for example, the spine of the page, okay, so you have individual pages instead of the folded ones. So what we're doing, they were putting them together, like here, and stitching it. And this is what you see in this drawing. So we looked at this sampler with a micro CT. Here you can see, and we went for this to Polytechnica, so to the Warsaw University of Technology at the Material Engineering faculty, where they have a large volume micro CT scanner. You can see here a sample book, positioned, detector on this side, X-ray tube on the other one, and the table that is moving to allow taking the different imaging. And this is what we obtained for the sampler book. So you can see above are pages where we have the so-called regular binding technique with the thread going in and out. This is the cover of the book that was put on top. You can see it clearly. Here you can see that there are the spines of the book that where they are, let's say, whole, and when there is no spine. In some of the pages, the different thicknesses, and then there are different threads. So these are just selected projections. On the bottom projections, you can see where we have this overstitching methodology, and it's clear from these images that are actually very sharp that we can distinguish these structures. So once we verify that we are able actually to get the information we want, we take the precious book and scan that book and try to figure out in which state it is. So you can see here the cover. The cover was actually in very good shape, and we couldn't do this of dismantling it because it was attached to it. The cover dates back to the last rebinding. So you can see here just a short GIF with the animation of the spine. But let's look at what we can learn from this. In the sketch, you can see that this is a structure that we were expecting. So you have a so-called end band here at the top, visible. These red vertical marks that can be here are the sewing bands. So these guys. There are some deep cuts in. There are 3 of them. And then there are some shallow cuts in the spine itself. And then here you can see that there are destroyed section spines because they don't show this rounded shape. We have also visible in some parts the thread here with a knot. And you can see also here this, some of these vertical threads and the canvas lining. So this is seen from the spine. And now we look at a different projection, XZ projection. So what can we learn here? So here we see again these deep cuts in the structure, which are most likely remnants of the original binding. You can see the vellum cover and the sewing band here, but also some little stitches here, which correspond to this overstitching method. So this corresponds to where the spines were gone, and they had to kind of be creative with their binding. Well, the sewing band here is the same one you see here in yellow. Also, this was evident from the visual inspection that the book was trimmed during rebinding, but it was possible to estimate how much was cut away. So you can see that the distance between these deep incisions is regular, 35 millimeters, but the distance to the top and to the bottom is different. This allowed to find that they trimmed 11 millimeters at the top, at the bottom, 12 millimeters at the top. And they also trimmed it on the other side. And we know this because when they rebound it, of course, vellum is kind of a material that changes with time. So when they dismounted it to rebind it, apart from mixing the pages and not putting them back in the correct order, they would not have a flat kind of surface for gilding because all the sides are gilded. So they just trim them off to have them flat and gild them. So the final size, which is this one, is 11.7 centimeters times 7 centimeters. And you can see also here that there were these damaged spines. So there are portions where the spine survived, and portions where the spine didn't survive. So this is what we expected. So to have the pages and then the thread going in and out. This is the other option, which is actually what we saw. That the pages were single pages stitched together. So we could exclude the original stitching being available, at least in many of the pages. Oops, sorry. So after this work, the book went for conservation. It was, as you can see, taken apart. And then this is, for example, partially damaged page where you can see that the spine here is missing in parts of it. It was rebound, and now it can open to more, let's say, than 30 degrees. And the paper was just accepted in Journal of Paper Conservation, on the conservation. And then we, once the conservation was concluded, we took again scans in order to see now that how the book should have looked like from the beginning. So you can see now clearly here the thread, the vertical thread, the sewing band, so the threads, the sewing bands, and the spines that were reconstructing during the conservation work. One projection. Now you can see clearly that what we couldn't see a few slides ago, all these loops with the dot in between are there, are clearly visible. So that's also where you can see them. You can also see in the other projection on the XZ plane that the thread, which is here highlighted in blue on top of the image, is going here in and out. So it is again clearly visible. These images, I should have said it before, you can see by yourselves that they are, let's say, less sharp. In a way, there is a lot of background that comes from the fact that the book has text inside, it has illuminations, so there are a lot of heavy metals which are actually disturbing the image when it comes to just studying the spine of the book. I'm going fast. Okay. During conservation, we had the possibility, there is a lot of material left over during conservation. And we got permission to take small portions, order of 10 milligrams, of sewing thread and carbon date it. So under the microscope, we handpicked, we handpicked these little pieces of thread from what looked like the different stages of the binding, and there was linen thread and there was silk thread. We went to the Gliwice radiocarbon and mass spectrometry laboratory, and where they can do carbon-14 dating, and they did acid-base acid treatment to these samples, and then combustion and graphitization in order to extract the carbon from the thread, and then they did the radiocarbon age determination. This is a picture of their spectrometer. These are the 4 samples that survived. Out of 10 samples, 4 survived the acid-base acid treatment. One is white linen. There is another one. Actually, all the 3 of them are white linen. The silk kind of disappeared during the chemical treatment. And these are the results, which are particularly interesting. So what do we see here? You have the radiocarbon determination. So these are basically fraction corrected fraction. It's basically the years before present in different units, okay, that you get from radiocarbon dating. And you have here the calibration curve, because on the abscissa you have the calibrated dates in calendar years. And it's a pity that in this period that we are interested in, the calibration curve is rather wiggly. So what do we have? We have here the result of the measurement with this red distribution, so the value with a sigma. And then you have that with Bayesian type of analysis. These are kind of well-established methods. There is the Oxford calculator that helps in this. You obtain basically a probability for the calendar year. This probability, you have it either with, you get it with either 68% confidence level or 95% confidence level. If we look, so we have this distribution, okay, so the upper here bars show you the calendar year when you look at 68% confidence level, and the bottom one for 95%. So let's look at the 95%. It tells us that there is a 75% probability that it is between 1489 and 1604. So this was a portion of the original 16th century linen thread binding, which was still present in the binding of the book, because this is too far from the second binding. The next sample, you can see it here. So you have again a different portion, of course, of the calibration curve, or also kind of wiggling, and then you have your distribution for the age, which intercepts the calibration curve in 3 parts. I mean, forget about this one, because of the wiggling of the curve, tells you that there is a non-negligible probability that it's from the early 20th century. But if you look at it with the 2 sigma probability, we have that the maximum, we have 40% of probability that it's between 1759 and 1830. So here, this central part. So this is likely, so there is a high chance, high probability, it's likely that this piece of thread stems from the last rebinding that happened between the 18th and 19th century. The third piece of thread that made it to the end of the measurements shows that something very interesting, because it helped with the history of the bindings of the book. So the values here of the intercept tell us that within 2 sigma, there is a high chance, let's say 62%, that this is between 1630 and 1666. So this is exactly 100 years, more or less, after the book was made, and about 100 years before it was rebound for the last time. And so this is most likely a sample stemming from the intermediate rebinding of the book. So this tells us that portion of the original linen thread binding were left over in the rebinding of the book, supporting in this way the history of the various rebindings of the book that was made during the conservation work, because while dismantling the book, you can really see all the different, let's say, hands that worked on it. Last but not least, it was a unique occasion. So you have such an object at hand, and during conservation, because you cannot do this when it opens to 30 degrees, but even it's difficult if it opens more, because you risk to put a lot of stress on the spine. So during conservation, we had a chance of analyzing the inks, the hues, the pigments in the manuscript. So every color, every different ink, there were inks of 3 different colors, red, blue, and black, and visually different ones. So they were making new batches of inks regularly, were analyzed by X-ray fluorescence spectroscopy methodology. And all of them. On top of it, this work we did in collaboration with the Interdisciplinary Laboratory for Archaeometrical Research at the Faculty of Chemistry. And we selected some of the illuminations. All of them was too much time consuming, so we selected the most interesting ones, which we mapped. So there is a spectrometer that allows you to take X-ray fluorescence spectra, so identify all the elements heavier than about silicon that are present point by point, and then you can reconstruct a map of the distribution of these pigments. So it's not hyper high resolution, but it allows you to study the distribution. I have here an example on one of the small capital letters. So this is the XRF spectrum of the color red here. You can see the laser pointer under my laser pointer where the measurement was taken. Several elements are identified. So these are the characteristic X-rays from copper, calcium, lead, gold, mercury, iron, and sulfur. Calcium is most likely due to the to the parchment, and but it's also present in several of the chemical compounds. It's a color red. There is mercury and there is sulfur. So this is vermilion, which is mercury sulfide. And of course, we were hitting, I mean, the beam spot is of the order of square millimeter or so. So you're not getting only the red color, but you're getting with the halo of your beam also. For example, the green is made out of copper. Here it's the spectrum of the color blue, where again you have a lot of calcium, but there is also copper, lead, gold, iron, and sulfur. Sulfur may also be due to the parchment itself. So in the color blue is blue. It's not cobalt blue, but it's blue made out of copper. If you put, these were individual points measured with high accuracy, with good precision. You can get very good spectra, measure longer. While when you do the mapping, you have to find a compromise between duration of the measurement and quality of the data. So the measurements are shorter because such a map has it's really a large matrix. So if here you have preliminary results, there is this letter D that we saw before, so the photograph, and then the mapping of the gold. So scale of intensity is here, blue is less intense, and purple is more intense. So you have, this is made out of gold. It was very popular gilding. Calcium is also under the gilding, the calcium that we saw before, to keep the gold leaves pasted to the page. You see here mercury. Mercury is basically in correspondence of the red flower. Red is a bit everywhere, but red is the base element for lead white. So it's here on the making of the letter D, calcium, and then copper, mostly in the blue, sulfur in the red, in the vermilion, and iron, which is present in many of the pigments. Sorry. So to summarize, micro-CT has proven to be an invaluable tool in diagnosing pre- and post-conservation of historical books, allowing the conservator to plan the course of the treatments and the intervention in a fully non-destructive way. The history of all the bindings that this book underwent during the centuries, and which was reconstructed during the conservation work, was confirmed by carbon-14 dating. On top of it, during conservation, we had the unique chance of performing several other non-destructive analyses. Data are still under evaluation, so hopefully in half a year or so we will have the final analysis. So I showed you only a glimpse of that. This was X-ray fluorescence spectroscopy to study the composition of pigments, hues, and inks, and the vellum support. Of course, you always take background. And the reflectance transformation imaging of the illuminations, which will allow to reconstruct the painting technique. We plan to continue these studies by studying other historical books, and we have discussions on the way with the study booth which has a very nice collection of old books to look at different geographical provenance and different time provenance. And if you would like to see the prayer book after conservation, it is now exposed at Wilanów. There is a temporary exposition on the Sobieskis and the Stewarts, from which I took these two photographs. And you can see that now it opens nicely. And before concluding, this is teamwork with different expertise that were in play, and a lot of people took part of it, so I would like to thank them. Thank you.
Thank you for this excellent talk, and we have time for some questions, please.
Of course.
I would have a question about carbon dating.
Yeah.
How do you know that it is not because of exposure to CO2, because due to way of heating living spaces in the previous ages by combusting wood?
I don't, even if the environment is contaminating. First of all, this thread was, if you see this book, the thread was deeply inside in the spine. So it was not really exposed to air. And
because of combustion. Combustion wood used to heat the space.
Yes, but the density of this CO2 is not high enough to penetrate deeply into the thread, for example. And the thread was really inside. It was taken after opening, cutting here, the spine, because there is a page that merges it. Today, modern books are kind of different, right? Maybe there is a comment, I guess.
Yes, I wanted to comment it. The thread that was tested, the white linen thread, it was actually glued inside of the spine, so it didn't have any contact whatsoever with the air or anything else until I dismantled the book.
So maybe I will ask a brief question. Because when you talked about these previous conservations,
Yeah.
You could see they were imperfect in some sense. They were good enough for that period, but not perfect, obviously. So do you think that if someone takes this book in 200 years, then he will say, or she, what have they done in 21st century? Or
Well, the conservator is sitting there, but first of all, what is done is documented now, because the conservation part is actually already published, and we will publish all the rest of the analysis. Great pain was taken in the materials that were chosen. Of course, certain choices have to be made, right? But the ethics in conservation has changed, the procedures have changed enormously. So at that time, to my understanding at least, they were not so careful, or maybe it was not in their really way of thinking to preserve. They just wanted to keep using it because it was obviously heavily used over the centuries. So a lot has changed, so I hope that they won't have anything to say. But at least it's documented which type of materials were used. All of these technical details are available.
So the last comment, the conservation is quite a new science. It was developed in 20th century, so all the previous rebindings, they were just performed as the bookbinders saw it fit. So they imagined some stuff, they thought that this course of action would be the best, hence so many difficult things that happened to the book in the 18th century. So the thing that I tried to do is I tried to make minimum interventions. I only reconstructed the spines, so I made like structural changes and used the least amount of materials that were like introduced. And the thing in the conservation is that you use reversible methods. So everything I did can be reversed, not to the 18th century and maybe not back to the 16th century, but still you can work on that book for many years after.
I have a question about the computer tomography. Sometimes I think this is you can use different X-ray energies.
Yeah.
Will that helps in the to gain better resolution or things like that in such case where you have these
Resolution
different
not,
materials?
but contrast. So we had some starting point for the voltage on the X-ray tube, because this is the first time the microtomography is used on books in this context of, study of the spine of the book in a systematic way for conservation purposes. But people have done micro CT scans of books to study, for example, books that couldn't be opened, or to study, there was a study on the cover itself to see what was inside when it's blocked. So we did have a guidance on the use of 100, 110 kilovolts is kind of optimal for this. But yes, there is that has an impact. The choice is important.
Can these methods cause microsublimation of ink?
No, that's not. Of course, we irradiate it with much higher currents that you would use on a human, right? But no, that's. It's not heating. Actually, we couldn't afford. You have to be very careful to find a compromise that also when we did XRF, we had very low currents of the X-rays in order to avoid any heating of the vellum, which is an hyper-delicate material. So in this sense, it's totally non-destructive. It would have been nice, for example, to look at the lead isotope ratios in the ink, but we decided not to do it because that might, it wasn't sure, but might have an effect on the ink. So that it was decided not to attempt it.
If there are no other questions, then let's thank the speaker again. And see you in January. Thank you.